Got it? Yep. So it is impossible to construct a table like this because Johnny draws more than 1,000 times, up to 1,000 times. It's impossible. So you have to use the central limit theorem. The solution lies in the central limit theorem. Okay. Okay, and you have to review the central limit theorem and review the example. Here the example. I will have you. I will have you answer the question. What is the probability that X bar lies between 1.95 and 2.05? Okay, and you can use the central limit theorem to standardize the X bar. To standardize, minus the population mean divided by the sigma over square root of 1,000. And you have to derive the value 2. Hey, the mean value here, hey, mu. 2 is the mean value, and sigma is the standard deviation. All right? And in the exam, it will be different. It depends on the scenario. All right? If it is 135, you have to use 135 to obtain the value of mu and also the value of sigma. It's different. It will be different, okay? And all you have to do is to update the value of sigma and mu. All right? Okay? So, and you see this last week? The calculation is simple. So all you need to do is go to the table. When we arrived here, the only thing we need to do is open the table and look for the area. Okay? And do the deduction, and then we will obtain this. And 95%. And so what is the conclusion? What is the comment we can draw about this probability? What is the comment we can draw about this probability? Hey, the probability makes statistical sense. All right? It makes statistical sense. All right? Okay. So what is our comment? All right? What is the implication? It is very likely that X bar lies in a small neighborhood of mu. You see this? Hey, it lies between 1.95 and 2.05 with very high probability, which is very close to 1. All right? So what is our comment? It is going to, you have to answer this question in the final exam. It is very likely that X bar lies in a small neighborhood of mu equal x2. Okay? Hey, how do you say 我住在附近? You live nearby? No. I have a better word. I have a better sentence. How do you say 我住在附近? Do you speak Chinese? How do you say 我住在附近? In English, I live in the neighborhood. 我住在邻近区域。I live in the neighborhood. Okay? So it is very likely that X bar lies in a small neighborhood of mu. Sorry, this is 2.05. Hey, here it is 2.05. So this is a small neighborhood of mu equal to. Here, it is 2.5. And here it is 5. And this part is a small neighborhood of 2. All right? Okay. Okay. The figure is not good enough. Let me revise it. In fact, it looked like this. And this is 2. And this is 2.05. And this is 1.95. And the area under the curve is 0.95. And this is distribution of X bar. Hey, the shape is sharper. All right? Okay? Yep, here. So that's the end of this section. So let us go to the next section, subsection, okay? Please go to the section 6-4. 6-4, yes. 6-4. Let me repeat the comment again. In a small neighborhood, of a mu equal 2. All right? Okay. Okay. So next section, subsection here. 6-4. The normal approximation to the binomial distribution. All right. A review of the central limit theorem. Okay, let x1, x2, all the way to xn be independent and identically distributed random variables. Such that ex1 equal ex2 all the way to exn equal mu. And that variance 1 equal variance 2 equal variance xn sigma square. Then x bar minus mu divided by sigma over the square root of n is approximately normal. The standard normal. Very close to the standard normal. Okay, that's what we learned last week, right? Where x bar equal the average of the n random variables. All right, that's the central limit theorem, right? Independent and identically distributed. Hey, and we will use 3 letters for short. IID. So next, when you see IID next time, you have to know it is I is the first, okay? First word, independent. Second word, second I, second word, identically. And third word, distributed, IID. I forgot why here. Why, okay, independently distributed random variables such that, okay, you got it? You got it. Understand? So, hey, sigma square is the variance of the common variance of x1, x2, and xn. But here, it comes with no square, all right? Only sigma. And here it is the square root of n, which is the sample size. And recall that now let us focus on the case that xi is distributed as Bernoulli. Okay, Bernoulli, which is P. And such that EI1 equal EI2 all the way to EIN is the parameter P. And variance I1 to IN, the common variance. Remember? Is the sigma square, and this is mu. Okay, it is PQ where Q equal 1 minus P. Okay? Hey, that's what we learned before, long time ago, early in this semester. All right? Hey, mu here is the expectation of the common expectation. It's P. But in a central limit theorem, it is mu. Hey, they are the same thing. Mu is the mean value. Mu is the mean value of I1, I2, all the way to IN. And it can be shown that the mu value is in fact P. And the variance of I, of each I, is P times Q, where Q is 1 minus P. All right? Okay, so we have the central limit theorem. The central limit theorem holds for I1. The central limit theorem holds for I1, I2, all the way to IN as well. Okay? I1 plus I2 plus IN, the average, minus mu divided by the square root of sigma over n. Hey, this is equal to x bar, I bar. Here I use I, not x, but the theorem holds as well, I bar minus p, and mu is p here, and sigma is p q here. Oh, don't forget to take the square root. So sigma here is the square root of p and q, p times q. All right? So by the central limit theorem, it is very, very close to the normal distribution. That's the central limit theorem for the Bernoulli random variable. All right? That's the central limit theorem. Okay? Yep. So hey, the central limit theorem also holds for I1, I2, all the way to IN as well. Hey, this is always the mean of n random variables. Here we use I bar. Hey, if it is x1, x2, all the way to xn, hey, here it is s bar. But now it is I use I bar. And mu, hey, mu as expressed upper right, hey, it is p. And sigma is the square root of p times q. Okay, that's the central limit theorem. What time is it? What time is it? Yep. And hey, why Bernoulli? Why Bernoulli random variable? Hey, Bernoulli random variable is the outcome of binary result, binary outcome experiment. All right. Suppose that you are, what is the example I used for Bernoulli example? Bernoulli random variable. Hey, Bernoulli, what is the example I used? Suppose that you graduate and work a few years, and your parent force you to attend a blind date, 相亲. Either you success or you fail. Okay? Or you apply for a job after you graduate. If, for example, you apply for a TSMC, okay, 台积电, all right? And either you success or you fail. That's a binary outcome. Only two results, either success or fail. And the success, the probability of having a success, make a success, it is P. And the probability of the failure is 1 minus P. So it is a Bernoulli random variable. It is either, hey, here, it is either 1 or 2, or 1 or 0. Hey, it is either 1 or 0. Each one of them can be either only 1 or 0. Here. 0 or 1. Only two possible outcomes. Right? Okay. 10-minute break. See you later. And the central limit theorem holds for any random variable, not necessarily only Bernoulli, but here we focus on the Bernoulli random variable. Okay, so always keep in mind, this hour and the previous hour, we focus on the Bernoulli random variable, okay? And it is going to appear in your final exam. All right? Here. Okay. So I wanted to rewrite. I want to re-express the formula. Okay? But observe that. Hey, here, observe that. Here. Observe that. I bar minus mu and sigma, it is n x1, x2 all the way to xn, right? Okay, minus p. Hey, here it is square root of n, square root of p over q, and then p and q. And here times n. Also here also times n, and okay, and nothing gets changed if both term timed by n. Okay, so if we times n here, it is n p q, and if we, sorry, it is I, not x. It is I, sorry. I1, I2, all the way to IN. All right. And it is I1 plus I2 plus all the way to IN minus m times p. Okay. And it is very close to 0, 1. All right. And it is equal to also equal to x minus mp. Now here comes x. But what is x? All right. Where x is equal to I1 plus I2 plus all the way to IN. Okay. Okay. Sum of n Bernoulli random variable. Okay. Okay. And it is equal to, hey, binomial. What happened? Eh? Oh! Ah! Hey! Oh my God. Hey! Oh my God. Ah! Observe that. All right. I bar minus mu divided by square root of n sigma equal to n I1 plus I2 plus all the way to IN dot 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 plus IN minus P and it is equal to I1 equal to I1 plus I2 plus all the way to IN minus NP divided by the square root of NPQ, which is very close to the normal distribution. So it is 1x bar x minus NP divided by NPQ, which is very close to, also very close to normal standard normal, where x is the sum of n Bernoulli random variable okay. And it is equal to, hey, here, the key point, binomial NP, hey, NP, all right? Binomial distribution. Remember, what is the probability distribution of a binomial random variable? Remember? Okay. And probability, 哎啊，很想飙脏话。I have to write it here, just in case. Observe that. Hi. Equal. And this one times n, and this term times m as well. We have minus NP divided by NPQ. All right, very close to the standard normal. And here, the sum of I1 to IN is now replaced by X. So it is NPQ. All right, where? Yeah, I save it just in case. Where X equal to I1 all the way to IN equal the sum of n Bernoulli random variables, which is called binomial. and P. Here, N is this N. All right? And P is this P. All right? Let me, okay. You got it? Any question? So if you don't have any question, then let me, okay. So note that. This is going to appear in the final exam. Binomial 1p is exactly the same as a Bernoulli random variable. Okay, and now we will apply this formula, apply this theorem. Okay, let's go to the example that Johnny take the exam of 50 true and false question. Example. And this example is going to appear in the final exam. Johnny. Answer. 50. True and false. Questions. Okay. By randomly select the answer. Selecting the answer by random. So what is the probability that he will answer 20 to 30 questions? Both included means, hey, 20 and 30 also count. All right. Correctly. When the answer is false, the answer is false, and he select the answer false. That means he answered the question correctly. And when the answer is true, his answer is true. That in this case, he also answered the question correctly. Okay. Okay. Answer. Let ij equal 0, 1 if Johnny answers correctly. Okay. For the 8th question. Answers the 8th question correctly. And 0 otherwise. All right? Okay. Then, the jth, not I, the jth. Then ij is distributed as Bernoulli. And because there are only two choices, true and false, so he will not answer the question correctly with probability 1/2. So the P here is 1/2. P here is 1/2, right? 0.5. Okay. And now, x equal I1 plus I2 plus all the way to I50 is distributed as binomial. 50 here and 0.5. Okay. Binomial. All right. Attention, or you will be sorry, because it is going to appear in the final exam. You are not paying any attention. Some of you. Many of you. And now the desired probability is probability 20 less than or equal to x less than or equal to 30. All right. Okay. So probability equal, hey, now use the central limit theorem here. This is what we need. Before we can use the standard normal probability, we have to standardize the binomial random variable. Here, the thing to minus is n times p. Here. Okay. Why n times p? Because here it is p and we times n. So we have x times minus n times p. And if we times n here, and it becomes the square root of npq. So let us standardize. Let me make a screenshot here. This one. This is what we need. All right. Because we need to standardize. I'm afraid you will forget the formula. Yeah. Okay. And safe. It's very dangerous. Yep, here. And also, let us standardize before we can apply the central limit theorem. 20 minus MP the square MPQ, and nothing get changed. We if we do the same thing to all the three terms, to each of the three terms. All right. So it is 20 minus 50 times 1 over 2. And now it is 50 times 1 over 2, 1 over 2. $30 minus 50 minus times 1 over 2. Now it is probability. Now it is very close to the standard normal by the central limit theorem. Okay, and here it is. Let me see. Let me see the value. I need to calculate. I need to calculate, right? 1.414 minus the same 414. Unfortunately, the table is only available for 2 decimal places. So we can only look for the number 1.41. Hey, ignore this one. Okay, ignore this. We can go to the table and look for the number, the critical number, 1.41. Okay, 1.41. So please go to the table. Go to the table. Go to the table. Yep, here. The normal table. Right? The normal table. Here. This one. I think this table is the same as that in your textbook. 1.41. Okay. What happened? This one is better. Hey, what happened again? Oh, yeah, here. Okay. Go to 1.41 here, 1.4. Hey, here. Goes to the leftmost column with 1.4. This is 1.40 and this is 1.41. So it is 9207. That's the probability we need. So here it is. Go to your table, 9207. So it is 9207 here. So it is 9207 minus 0.0793, right? Four and one and 4 and 8. So it is 0.0793. A414, right? Let me wipe it off. All right, that's the probability we need. And now it's very easy. All you need to use is the central limit theorem and the table. And now if you know, but one thing I have to tell you is that the number, the approximation. Hey, this is a hey, you see the two dot here? The two dot means that this probability is the approximated probability, not the exact probability. Approximated probability based on central limit theorem. Approximated by the central limit theorem, which is the fake one, fake probability, not exact. Now, but the exact probability is equal 50 times x, x to from 20 to 30, and 1 over 2 power x, 1 minus 1 over 2, 50 minus x, okay? That's the exact probability. Use Excel. Okay, let us see how good is the approximation. We need to see how good is the approximation. I have to tell you that the approximation by the central limit theorem so far is not good enough. You will see why. And because you are taking the exam at home online, you have the access to a notebook or desktop PC, personal computer. Okay, you need to use the Microsoft Excel to calculate the exact probability. Okay, because you are taking the exam online. Don't complain. And I will give you the method to calculate, to compute the exact probability. I will give you the Excel file, right? So please go to the Microsoft Excel here, and I will give you the file. Okay, don't worry. But you have to answer my question with this, with the formula here. Okay, equal. Oh no. From 0, 1, 2, 3, 4, 5. Okay, all the way to how many? Hey, here all the way to how many? To 50. Because he answers the question 50 questions. All right, and this is the formula. 50 choose X, and it is COMBIN. Okay, 50. This one times 1 over 2 to the power X times 1 minus 1 over 2 to the power 50 minus X1. 50 minus X. 50 minus X. Here, right? Oh, no, not to the power. To the power. Yep, which is a very small value. And if you sum them up, it will be trivially 1. Okay? It is 1. But because total probability of any random variable is 1. So this means that the probability we calculate is correct. All of them, they are all correct. All right? They're all correct. Now, let us sum the probability from 20 to 30. Here from 20 to 30. Hey, not this one, 20. Not this 20, okay? This 20. All right? This 20. And not this 30. Not this one. Not this 30. It is this 30, okay? So sum them up, and here's the answer. The exact probability is and unfortunately, we can see that the approximation is not good enough. Why? Because the probability approximated by the central limit theorem is 0.84 something. And now it is 88 something. It's so different. Not close enough. Okay? Not close enough. How to correct the problem? We can correct the problem very easily if you can look at the figure. Now let me plot the binomial distribution here. Yep. Yeah, this is the binomial distribution. The binomial distribution here, bigger. Here, here, and here, and here. And this is a fake figure, just for demonstration, okay? Don't complain, and don't tell me it is ugly. For example, this is 20. And this is 20. And this is 30. All right? And now, this is the binomial exact probability. Exact binomial probability. Okay? The red shaded area. Okay? And what is this? This is the normal approximation probability. This is the probability approximated by the central limit theorem. Here, and here, here. Like a Christmas tree, right? Is it like a Christmas tree? Huh? And this is the approximated by the central limit theorem. and this is it. Okay, so what is the difference? What is the difference? What is the difference between the two shaded area? What is the difference between the two shaded areas? Hey, please tell me the difference. Yep. No, that's not it. The difference is obvious because the binomial probability, included this part. Okay, half a step right to 30, and half a step left to 20. And what is the so what is the difference between the two areas, two shaded areas? The difference is the half part of this and the half part of this, and this is why this is 84 something, and this is why that's 88 something. All right, the red part is bigger and the green part is smaller. So this is why the red part is 0.88 something. This is the red part. This is the red part, and this is the green part. Okay, so this is the red part and this is the green part. Okay, this is the red part. All right, the red part area. Okay, this is the green part area. And the green part is smaller and red part is bigger. You see that? Okay, and this is 0.88 something. What is it? 10798. And what is this? 0.84. Okay, so all we need to do, all we need to correct, to do for correction is half a step to go further, half a step to right to 30, and half a step go further to the left of 20. So this is called continuity correction. Continuity correction can fix the problem. Okay, so this is the probability. So if we move half a step right left to 20, it is 19.5, and it is 30.5 here. So the same, the rest remains the same. Minus. Okay, and now it is again the, hey, don't forget the dot because we are approximating. And now go to the table. And before go to the table, we have to do some little calculation. You will have to do the the continuity correction in the final exam. All right. Here. What is it? It is 1.56 minus 1.56. All right. Is that so? So what is the probability? Please go to the table again. Go back to the table again. The table here. 1.56. Hey, what happened? The normal table. Hey, this one. Yeah, 1.56. 1.56. 1, 2, 0, 1, 2, 3, 4, 5, 6. This one. This one. 156. This one. 9406. Here, 9406. So it is 9406. Minus 0.0594. All right. Let me finish. It is equal to 0.8812. Hey. Now, after continuity correction, it is much better. Is it much better? So what's the difference? Please tell me. What's the difference? The continuity correction? This answer is close to which one? The upper one or the lower one? The upper one. Hey, it is 0.88 something, 88.1 something, and this is also 0.881 something, 1, and here it is 1, 2. Is it close? Much better. Very close. Excellent and excellent. Okay. Let me use the word excellent. Correction. And you will need to do this in the final exam. Understand? So this tells us that, hey, the binomial distribution can be approximated by the normal distribution. Okay, we can use the central limit theory to calculate the probability related to the binomial probability. Okay. All right. So let me before I forget, let me upload the file here. The exact binomial probability. Exact binomial probability. Okay? Not here. Here. It's here. Okay? Exact binomial probability. Here. And let me upload first before I forget. Here. Yep. Statistics. Your class. I will make a formal announcement. Here. Lecture note. Right. Oh, later. Yep. Let me also use this to plot the binomial probability. This is why we can use the normal distribution to approximate the binomial probability. They are, they are relative. They are so close. Up here. You see this? What is this? This is the binomial probability. And if you remove the space between the two bars, what did you see? What did you see? Hey, anyone raise your hand to volunteer? Tell me what is the figure look like? What does the figure look like? The normal distribution. Why? Because it is symmetric and bell-shaped. Understand? And this is why we can use the normal distribution to approximate the binomial probability. No Chinese. And this is why, let me copy, and paste. Yeah, here. Plot of binomial 50 1/2 distribution. Which is look so much like the normal distribution. Okay? All right? For some mu and sigma square. And this is why we can use the normal distribution. Hey, please give me a few minutes. To approximate, I will make the roll call. Don't panic. The binomial probability. All right, and I will give you also this chart. All right. Yep. Safe. And here. I don't panic. Where is it? This one. Yep. And also this one. What day is it? Hey. Save us. So what day is it today? 21st. And yep, this one. And save in PDF format. Okay. Yeah, this file. Ha. This file. Where is it? Yep, this one. Yeah, for today. Very good. Excellent. Hey, in the final exam, I will have you calculate the exact probability and then also the probability approximate by the central limit theorem. And I will also have you answer the relation between binomial probability and also the binomial distribution and also the Bernoulli distribution, binomial and Bernoulli. Hey, they are different. They spell differently, okay? Different words and different distribution, but they are so closely related. So roll call time. Here. Yep, here. Roll call. Um, 6 minutes, 6 seconds. Don't pass the code. Okay. Hey, come to me if you need need to make up. What? 第二次. What is your name and a seat number? No. Seat number. Okay. Yep. Oh no, you are too late. The first time you were not here. Seat number and name. Seat number. Yep. 对啊，因为你只有2个选项啊，就乱猜，就是0.5啊。对，那固定的啊，那跟那个没有关系啊。对。如果是4选1，那就要带0.25啊。选项的关系啊，就1/2啊。如果是选择题就1/4啊，这样你懂吗？嗯。不，努力只有做1次实验啊，2项 binomial 是做 n 次实验啊，那不一样啊。嗯。一个做1次啊，一个是做 n 次啊。那1次你做 n 个，然后把它加起来，那就是 n 个伯努利了，n 个binomial。嗯。